Hi everyone, Mrs. Jones here. In this video, I'm going to give you a quick introduction to a concept called systems of equations, as well as one of the ways that we can solve systems. What I first want you to do is take yourselves back to chapter 6 and the glorious days of frozen yogurt when we looked at Yogo Joy and an equation that was quite similar to this one. Keep in mind that we said X was going to be our ounces of froyo, and we said Y was going to be our cost. We then said this 3, or the number that was represented there in the coefficient, is our slope. Hopefully that's a familiar word. And in this situation, we're saying that every ounce costs $3. And then we looked at the 2 as being our y-intercept or starting value. And again, hopefully a familiar word. And the 2 was represented by what you're starting with. So even if you didn't buy any frozen yogurt, that cost of the cup was $2. So what I want to now do is compare Yogo Joy to Pinkberry. And you can see Pinkberry's equation is a little different. They're now saying that they're charging $2 per ounce, and it looks like the cost of their cup is $4. So what I've done here to try to help myself understand the difference between these two stores is I've graphed them because I think the visual component is really helpful. And this graph can tell us a lot of things. Keep in mind that X is ounce and Y is money or cost. And we can use this to interpret which one's the better deal, etc. But what I really want to focus on right now is at what point is the cost at both stores going to be the same? Meaning, how much frozen yogurt do I need to buy at both stores to spend the same amount of money? So I want you to pause the video right now and I want you to tell me where on my graph can I see this? All right, you're back. Hopefully you've agreed that the intersection point is what's going to help me here because that intersection point is the same information for both lines. But I want to be really specific and I feel like my graphing job isn't as precise as it could be. So I'm going to use Desmos. Hopefully we've all been to desmos.com and we can click start graphing. I'm going to graph my first equation of y equals 3x plus 2 for Yogo Joy, and then y equals 2x plus 4 for Pinkberry. If I click and hold here, I can actually change the colors to reflect closer to what we had on our slides. A few other tidbits. If I click this toolbar where it says graphing settings, I really like to be on projector mode. I just feel like I can see it better. I can change the label of the axes. So I'm going to say ounces, and I'm going to say cost as dollars, and then I can click. But I can't see my intersection point. So if I click and if I drag, it can appear. And then what's amazing about Desmos, there's lots of amazing things, but one of them is that it's actually going to calculate our intersection point for us. So I can click right here and a gray dot appears, as does, if I click the gray dot again, the intersection point, the coordinate of that intersection point. So 2 comma 8. Let's go back to our slides here and write that down. So our coordinate of the intersection point is 2 comma 8. Now with graphing these, interpretation is key. So let's add our labels. This means that 2 ounces is going to cost $8. That tells me that at both Pinkberry and Yogo Joy, if I buy 2 ounces of frozen yogurt, I'm going to spend $8 at both stores. So a system of equations, which is what we were just looking at, is this idea of more than one variable. So we've had x and y, and we need more than one equation. We had our teal equation and our purple equation. There's linear systems and there's nonlinear systems. Hopefully you recognize that we were just working with a linear system, okay, because we're looking at lines. Keep in mind that you have lots of different ways to be able to write lines. We have our slope-intercept form, which is y equals mx plus b. We have our standard form of ax plus by equals c. Now think about nonlinear systems. There's a couple of different things. We know about absolute value functions, right? We have our y equals a, absolute value of x minus h plus k. And then we have our parabs. Remember abs and parabs? We have our parabola, which was similar, but we square it, right? Keep in mind here that it's that vertex is our h comma k for both abs and parabs. So nonlinear systems can involve absolute value functions and parabolas. So the way that we can solve these systems is by graphing. And the key here, the key for our solution is by looking for intersection points. So if I give you this solution right here, or sorry, this system right here, I want you to think to yourself, is it linear, is it nonlinear? And how many solutions, meaning how many intersection points do you think there will be? So pause the video for a second, ponder these two questions to yourself. All right, you're back. Hopefully, we agree that this is going to be a linear system, which means we are going to have one solution. So let's take a look. Here we go. We have our two lines, and we can see that our lines are crossing right here at zero, or oops, sorry, going backwards at 2 comma 0. So the solution to this system is that point 2 comma 0. Let's try another one. So pause to yourself right now. Think, how many solutions are there going to be? How many solutions you think there might be? And is it linear or is it nonlinear? All right, you're back. So hopefully you've realized that we are going to be nonlinear here because look, we have a parab right here, right? So, but what we need to think about is that there's a chance, if we have a line and a parabola, there's a chance that that line might cross once, might cross twice, or might not cross at all. So we have to graph to be able to see that. And here we go. I've graphed. But again, this isn't that precise. So I'm going to go back to Desmos and I am going to see what I've done here. Okay, I've plugged in my two equations, and in fact, I do have two solutions, meaning two intersection points. Again, if I click on it, it's going to give me, I have 0, comma 2 as one solution, and 5, comma 17 as my other solution. So here, if I were to extend this, right, which we can assume it's going to happen, not very straight, but you get the idea, we're going to be 5, comma 17 as one of our solutions. And then remember the other solution was right here, which was 0, comma 2. All right, so there are different numbers of solutions depending upon your system, okay? You can here we have two solutions because those two blue dots are showing the two intersection points. Here's an example of one solution because there's one intersection point. And here's an example of zero solutions, meaning the lines or the nonlinear functions never actually cross. You're going to explore all of this a little bit more algebraically, as well as what do you think might happen when we have infinite solutions. So hopefully this makes sense. If you have any questions about graphing, let us know. But again, you're going to practice some graphing now, and then you'll learn some more algebraic approaches later this week and next week. Good luck.